Scene script. Have you ever pondered the nature of space and time? Let's take a moment to consider the world around us. Our lives are governed by the ticking of the clock and the space we occupy. But are these concepts as straightforward as we perceive them to be? Enter Albert Einstein, a man whose name has become synonymous with genius. In the early 20th century, Einstein introduced groundbreaking theories that challenged our conventional understanding of space and time. His theories of relativity, both special and general, were not just scientific milestones. They were revolutionary ideas that dared to redefine our understanding of the universe. Einstein proposed that space and time are not separate entities, but are interwoven into a single fabric, a concept he called spacetime. He suggested that the very essence of space and time could be distorted by the presence of massive objects. Einstein's theories of relativity, both special and general, revolutionized our understanding of space and time. These theories continue to shape our perception of the universe, leading us into a realm far beyond our everyday experiences. Diving into the realm of the extraordinary, we encounter Einstein's special theory of relativity. This theory, put forth in 1905, fundamentally changed our understanding of space and time. It's not as complex as you might think, so let's break it down. The special theory of relativity is based on two key principles. The first is the principle of relativity, which states that the laws of physics are the same in all inertial frames of reference. In other words, if you're in a closed box, moving at a constant speed, there's no experiment you can do inside the box that will tell you whether you're moving or stationary. The second principle is the constancy of the speed of light. No matter how fast you're moving, you'll always measure the speed of light to be approximately 300,000 kilometers per second. This was a radical idea at the time, as it means that time and space aren't absolute but are intertwined in a four-dimensional space-time. Now let's talk about time dilation, a fascinating consequence of these principles. Imagine you're on a spaceship traveling close to the speed of light and you decide to play a game of catch with a friend. From your perspective, the ball travels in a straight line from your hand to your friend's. But to an observer standing still relative to the spaceship, the ball follows a diagonal path, covering more distance. Here's where things get interesting. Since the speed of light is constant, and the ball has traveled a longer distance from the stationary observer's perspective, the only way to reconcile these observations is if time itself slows down on the spaceship. This is time dilation. In essence, Einstein's special theory of relativity tells us that time isn't a constant, unchanging entity. It can stretch and compress based on your speed relative to the speed of light. So the faster you move, the slower time passes for you. A truly mind-boggling proposition, isn't it? Now let's escalate to a higher level of complexity with Einstein's general theory of relativity. Imagine you're standing on the surface of a trampoline. Your weight pushes down on the fabric, creating a depression, a curve. Now, if you were to roll a marble across this trampoline, it would naturally be drawn towards you by the curve you've created. This is a simplified way to understand Einstein's general theory of relativity. Einstein proposed that the presence of mass and energy distorts the fabric of space and time, much like you standing on that trampoline. This distortion creates what we perceive as gravity. Instead of seeing gravity as a force pulling objects towards each other, Einstein presented it as a curvature in space-time that guides objects along certain paths. Everything in the universe, from the smallest atom to the largest galaxy, exists within this four-dimensional fabric of space-time. Massive objects like planets and stars cause a significant distortion in this fabric, creating a sort of cosmic well that objects fall into. Imagine the Earth moving around the Sun. According to Newton, the Earth is pulled towards the Sun due to the force of gravity. But in Einstein's view, the Earth is moving along a curve in the space-time fabric created by the Sun's immense mass and energy. It's like the Earth is a marble rolling around the depression you've made on the trampoline. This change in perspective has profound implications. It tells us that the universe is not just a stage where events play out, but an active participant, its very shape influencing the motions of celestial bodies. Moreover, the general theory of relativity predicts that time itself is affected by gravity. Near a massive object, time slows down. This is not just a theoretical prediction, it has been confirmed by precise experiments. In essence, objects don't just fall towards massive objects, they follow the curves in space-time that these objects create. You might wonder, how do these abstract concepts influence our everyday life? Well, it's astonishing how these seemingly esoteric theories of relativity have profound implications and applications in our real world. They have not only reshaped our understanding of the universe but also fueled several technological advancements. Let's take the Global Positioning System, or GPS, as an example. This technology, which we heavily rely on for tasks as simple as finding a local cafe or as complex as navigating a transatlantic flight, is a real-world application of Einstein's theories. The GPS system works by using the concept of time dilation, a direct consequence of both special and general relativity. Satellites orbiting Earth send signals with time-stamped information back to our devices. The time it takes for the signal to reach us helps determine our position. However, here's where things get interesting. Time and space isn't the same as time on Earth. According to special relativity, a clock moving relative to an observer, in this case the orbiting satellite, will appear to tick slower. On the other hand, general relativity tells us that a clock in a stronger gravitational field, like Earth's surface, will tick slower than a clock in a weaker field, like the satellite in space. These two effects are in opposite directions. The net effect is that time on a GPS satellite actually ticks faster than a clock on Earth, by about 38 microseconds per day. This time discrepancy might seem insignificant, but if not corrected, our GPS coordinates would be off by about 10 kilometers per day, and that's just one example. From understanding the fundamental nature of the universe to enabling precise timekeeping, the theories of relativity continue to impact our lives in ways we might not even realize. Without taking into account these theories, our modern navigation systems would be off by kilometers. So next time you use your GPS, remember, it's all thanks to Einstein's genius. So, have we unraveled the enigma of space and time? Not entirely, but we've certainly made strides. Let's take a moment to revisit the key points we've discussed. Albert Einstein's theories of relativity, both special and general, have significantly altered our perception of the universe. They've shown us that space and time are interwoven into a single continuum known as spacetime. They've also revealed that massive objects can distort this continuum, creating what we perceive as gravity. However, while these theories have brought us closer to understanding the cosmos, they've also presented us with new mysteries. For instance, if spacetime is a fabric, what happens when it rips? And how does quantum mechanics, the study of the very small, reconcile with relativity, the study of the very large? In the grand scheme of the universe, we are but learners, forever seeking to understand its profound secrets. Our quest for knowledge continues, fueled by the enigmatic nature of the universe itself. As we wrap up our brief journey through space and time, let's pause and take a moment to reflect on the remarkable theories we've delved into. Albert Einstein, with his theories of special and general relativity, gave us a new lens through which to perceive our universe. The very fabric of space and time was redefined, casting aside the traditional Newtonian view and replacing it with a dynamic, interconnected cosmos where space curves and time dilates. These theories aren't just abstract mathematical constructs, they have profound implications that touch upon our everyday lives. From the GPS technology that guides us to our destinations, to the cosmic wonders we marvel at, the fingerprints of relativity are found everywhere. Yet, the true beauty of these theories lies not in their practical applications, but in their sheer intellectual elegance. They challenge our intuition, defy our common sense, and invite us to embrace the delightful absurdity of the cosmos. As we stand on the shore of this cosmic ocean, it's only natural to feel a sense of awe and bewilderment. The universe is vast, mysterious, and operates on principles that often seem alien to our human minds. Yet, it's this very mystery that beckons us to explore, to question, and to ponder. So, I invite you to keep exploring, delve deeper into the theories of relativity, venture into the quantum realm, or ponder the mysteries of black holes and dark matter. There's a universe of knowledge waiting to be discovered. And remember, every great journey begins with a single step. The world of physics is a fascinating one, filled with enigmas and paradoxes. It challenges us, confounds us, and yet, it is this very complexity that makes it so captivating. As we unravel the mysteries of the universe, we're not just learning about the cosmos, we're learning about ourselves. Remember, the universe is under no obligation to make sense to us. Yet through science, we strive to decipher its enigmatic language.